Now let's take a look at a beam with distributed load applied to it. A beam like this, with these boundary conditions, may be exposed to a distributed force like that, Qx. And we can discretize this beam element into one element with two nodes, node 1 and node 2. And each node, just like before, will have its own moments, rotations, forces, and displacements. And let's assume that the length of this beam element is L. One method to solve beams with distributed forces is called work equivalence method, which means distributed work is equal to discrete work. Before we describe what each of these works are, let's just talk about what a work is. A work in mechanical engineering or in physics is called force times displacement, or FD. Now, we have a distributed force. If we multiply it by displacement function and integrate it over the length of the beam, gives us the distributed work. So this is the distributed work. And if I multiply each of these forces by their corresponding displacements, so m by phi and f by d, and add them together, I end up with the right-hand side of the equation, which is the discrete work. So let's remind ourselves of what this v, the displacement function, was. We assumed a third order polynomial, c1x cubed plus c2x squared plus c3x plus c4 for the v, and that's what we will put in here. And q is the property of the distributed force which is applied to the beam. And we also know the c1, c2, and c3 from previous slides or lectures, which if we put there, we can find this integral. So let's find the distributed work. It's this integral from 0 to L, qx times vx dx. Qx times, this is the expanded vx, c1x cubed, c2x squared plus c3x plus c4 dx. And if we assume a constant q in the negative y direction, this equation becomes like that, minus q times those terms. And if we integrate that, we'll have minus q times c1 over 4x to the 4 plus c2 over 3x cubed plus c3 over 2x squared plus c4x from 0 to L. If I put 0 in x, it will all become 0. So I only need to put the L there, and I'll end up with minus q times c1 over 4 L4 plus c2 over 3 L cubed plus c3 over 2 L squared plus c4 L. Now if I put those c1, c2, c3, and c4s in that equation, I will end up with this format of the distributed work, which looks overwhelming. But what that means is that this distributed work, which I've shown with brown in here, should be equal to the screen discrete work. So this is the discrete work. If I rearrange this brown equation so that I only have coefficients of d1y and d2y, phi1y and phi1z and phi2z, that would tell me the relationship between m's and f's with q, l, and the left-hand side of this equation. So I want to find the relationship of m's and f's with ql. And that's what we do in the next slide. We find this. F naught, which is called the equivalent nodal force, which is F1y, M1z, F2y, F2z with EQ, showing that this is equivalent nodal force, becomes equal to minus QL over 2, minus QL squared over 12, minus QL over 2, and QL squared over 12. What I have done basically is to expand this Brown equation so that I will only have one of each terms, d1y, d2y, phi1z, and phi2z. And then by simplifying that, I find the equivalent of these nodal forces. And that's why it's called equivalent nodal forces. Now we'll use this equivalent nodal force to continue solving for a beam which has distributed forces applied to it.